All right, so today we're going to look at why we use what we use. Actually, it's for the next 2 weeks we're going to do that. It's the book's chapter 2A, if you're following along in the book. Our House of Representative Chuck Fleischman has announced a contest sponsored by the U.S. Mint due to the popularity. Remember those special quarters they had? It was first state quarters and then it was special cities or something like that. I don't know. The U.S. Mint would like to introduce a $50. So they want students to create a design and actually tell them what kind of metal to use and what it should look like and how big it is and stuff like that. So every aspect of it needs to be designed by you. Now, this is not for reals, but this is something that could have happened. Okay, so what we're going to do is we're going to look at the chemistry behind materials. And so that by the end of this 9 weeks that's coming up, I'm going to give you a project where you design the $50. And you have to tell me what kind of metals to use it, and you'll even have to tell you how much it'll cost, because it really needs to cost less than $50. Okay, that's the whole problem with the penny. The penny no longer costs a penny. Every time they print a penny, it costs 2 or 3 pennies, yeah. So you will learn about certain materials and how they're used and how they're obtained. All right, so some of the things we're going to cover this chapter: the difference between physical and chemical properties, which is a review, difference between metals, nonmetals, and metalloids, the history of the periodic table, and the arrangement of the periodic table. How to use the periodic table to predict the personality. We can predict its identity by just knowing how many protons it has, but its personality comes from the number of electrons. So by the end of this chapter, we'll be able to map out the number of electrons in order to know why does an atom act the way they do. Now, I'm not going to explain this to honors chemistry until January, and they're dying to find out. So don't tell them. This is our little secret. Even the other general chemistry classes won't learn this until next semester. I just like to teach it early. The physical properties of elements that demonstrate the patterns within the periodic table. And the electron configuration is what I was telling you about, how we will map out the electrons and where they're located and what they mean. Okay? So cool stuff coming up. Here we go. Why is the Statue of Liberty made of copper plates? Why copper? Do you know that the space shuttle, back when it was functioning, had gold wiring in it? Why? Why is hydrogen and oxygen used as rocket fuel? Why? Well, the fact is that these substances are just perfect. Why do they use gold wiring in the space shuttle but not here for our building? Why do we use copper? Does anyone know? Gold is a whole lot better at conducting electricity. Okay, if we were using gold, the chances of there being fires would be greatly diminished. Unfortunately, no one would be able to afford a house because it would be too expensive. Then the space shuttle, since we're already spending millions and millions of dollars on space shuttles, we can afford the gold. Not to mention, if there was to have a fire in the space shuttle, it's not like we would have firemen up in space that can come and put it out. So they really, really, really do not like fires in space. They've had them before, and they don't like them. What are physical properties again? Who can refresh our memory? Jeffrey. Okay, those are examples. What is a physical property? Jackson. Okay, good. Okay, so they're physical properties that describe a substance without really changing what it is. So like he said, you can freeze it and then melt it. It doesn't change what it is. A lot of times they're just properties that can be easily measured about a substance. Odor. Does it conduct heat well? Color. Does it conduct electricity? Is it a liquid at room temperature? Is it a solid at room temperature? Is it a gas? What is its melting point? Those are all things that could be measured. Is it malleable? Is it ductile? Is it shiny? What are chemical properties? Give some examples of that. What are chemical properties? Asher. Okay. That's an example. What are chemical properties, though? Something that properties that describe how it changes with something else, how it becomes something new. Good. Describe how a substance acts when it's introduced to other substances. So how does it react with water? How does it react with an acid? How does it react with air? Here's a good example. These are modern pennies, and this is a penny that was minted back during World War II. And this is a penny after the same penny after being used for a few years. Okay, why do we not use zinc for pennies? It corrodes very, very quickly. This is a modern penny, and this is after the same penny after the same amount of time. So how much has copper corroded now? Not much. So what they do, we do use zinc pennies. So these are the kind of pennies that are being used now, but they put a copper covering on it so that it resists corrosion. It's still going to corrode, but it just won't corrode as quickly. What is the difference between physical and chemical changes? Physical change.
Impermanent.
A change in phase, so it's something where you change the material in some way without changing what it is. So you can make it go back. All right, good. And a chemical change, it's not reversible. That's it. You hard boil an egg, the egg isn't going to turn back raw anymore. Okay? It's over. It's a chemical change. All right, so chemical or physical property. Some metals become dull when exposed to air.
Chemical.
Let's raise our hands. Serenity's got the first one, chemical, because it's being exposed to air. That's the key thing. Bailey, mercury's high density in liquid state at room temperature makes it useful in barometers. When you put it in a barometer, does it change what it is? So it is a physical or chemical change? Physical change. Metals, when pure, have a high luster. They're shiny. Randy? What? Physical. Okay, just because they're shiny, what does that mean? Is it becoming something new? Archaeologists uncover golden artifacts, and they're untarnished, but iron is very difficult to find because it tends to rust. Hunter? Chemical. The iron is rusting with oxygen, some of the other gases. Here's an example of chemical or physical change. Tell me.
If we combine one gummy bear, which is composed mostly of sucrose, with molten potassium chlorate, a violent reaction occurs. A surprising amount of energy is released by the reactants, and in the process, their atoms and molecules rapidly rearrange to form the products carbon dioxide, water, and potassium chloride. The reaction is said to be product favored.
I call this death of a gummy bear. Okay, would you say that that is a chemical or physical change? Chemical change. How about hardness of diamonds enable them to be used as drill bits? Physical. Going back to the gummy bear, you realize that happens to you in your cells every moment of every day. But it happens on a much smaller scale. Okay, that was a lot of sugar, and the molten potassium chlorate represents a huge supply of oxygen. Okay, so we can't burn gummy bears that quickly because A, we don't ever, our cells don't ever get that much sugar in it at one time, and B, we can't get that much oxygen in at one time. But C, if we did, then we would burn our cells out. That would be kind of fun. Metals are ductile. They can be drawn into a wire. Isaac? Physical? Okay, so what? It's now a wire. It's still the metal. You shouldn't use silver utensils to handle sulfur containing food such as eggs and mustard, since the silver will tarnish. Kelsey? Chemical, because that tarnish is actually a rust covering where the silver has reacted with the sulfur. High melting point of tungsten makes it useful for light bulb filaments. Spencer? Physical. Okay, so wow, it melts at a high temperature. Does that explain how it changes with something else? Metals are typically much better conductors of heat and electricity than are non-metals. Devon. So what are the metals reacting with in order to conduct electricity? The answer is nothing. So if it doesn't require for it to react with anything in order to conduct electricity, then what must conducting electricity be? Physical. Magnesium ribbon. Perhaps you've never seen this, but you've seen it on television. Magnesium ribbon of a photo flash cube ignites in oxygen around it when you snap a picture. Homecoming king. Chemical or physical?
Are we on J?
Yes. He was dreaming about having, that moment in which they said his name.
I'm gonna go with.
How about ignites in oxygen?
Chemical.
Okay, because it ignites in oxygen. All right, so what are two reasons why a superior substance may not be used for a certain job? For example, gold, it would be awesome if it was used for our electrical wiring. It would bring down the incidence of electrical fires. Why don't we use it?
It's really expensive.
It's really expensive. What's another reason why a particular substance, though it may be superior, is not used?
There's not enough of it.
You might
Serenity?
overdo it.
What?
You might overdo it.
It may have overdo it. Okay, I would say that another way of saying it is it may have some undesirable side effects. When I think about that, I think about those all medical drug commercials. Have you noticed? They spend about 30 seconds telling you about how awesome they are, and then they spend a minute and a half telling you about how they can kill you or make you go nuts. Yes?
There are depression medicines that make you suicidal.
I know. My wife encountered one of those. I said, "No, sweetheart, I don't think this one's working for you." Okay, I just want to die. Okay, yeah, I don't think this one's working. We will call the doctor. So I call the doctor. I go, "I don't think this one is working. She wants to die." "Oh, no, that's not working." "Yes, it's not working. That's what we've said." Why is zinc being used today for copper pennies? Zinc is awesome. It is cheaper. And now, unfortunately, back in the 1980s when it switched over from copper pennies to zinc pennies, a zinc penny was actually about a penny, maybe a little less. But now a zinc penny is actually more expensive. So the U.S. Mint is trying to figure out a way in which they could get rid of pennies because they're losing money every time they mint a penny.
That's pretty funny.
It is less expensive and just as hard as copper. Actually, the density is close to copper, so it feels the same, close to the same.
You can make styrofoam pennies.
Styrofoam pennies, but then the density would be way off.
Wouldn't it break apart?
Yes. Zinc pennies were used during World War II because we were using a lot of copper for the war effort. Why were they not used later? Because they corroded much faster. They are higher up on the activity series. Activity series is something we will talk about in a coming chapter. How was the problem solved in modern times? So we needed to use zinc pennies again because they got too expensive. Serenity, we covered it in copper, which is rust resistant. Okay, so there is a modern penny. If you were to cut it in half, you would find that the inside is silver color. It's not silver, it's zinc. And the outside has just a thin covering. Yes?
Why does it say it's zinc coated when it's copper coated?
It should be copper coated. That's a typo. Sorry. All right, so here we go. Get your notes ready. Our two targets for today, I can identify a substance as metal, non-metal, or a metalloid based on physical properties. And number two, I can use the periodic table to determine if an element is a metal, non-metal, or a metalloid. So, how many elements are known today? 117. maybe 118. They've not confirmed that. Of these, how many are important to us? About 40 are important to us on a daily basis. 40 are important to us. What are the two major classifications of elements? Metal and non-metals. And why are they classified in those two distinctive ways? Well, metals have certain characteristics, and non-metals have almost opposite characteristics. The characteristics between metals and non-metals are very, very different. We can almost say that metals are from Mars and non-metals are from Venus. All right, so let's look at the characteristics of metals and non-metals and how they differ. So it's going to be a chart and go back and forth. Here we go. Metals are shiny, non-metals are dull. Metals can be like Play-Doh, pounded into whatever shape we want them to look like. You do that with a non-metal, it'll break apart into a million pieces. It is brittle. Metals can be drawn into a wire. Remember doing that with Play-Doh? Usually you had some kind of mold, like a hole, and you push the Play-Doh through the hole and it became a wire on the other side. That's ductility. So Play-Doh is ductile, but why is Play-Doh not metallic? Why is it not considered metallic? Well, it doesn't have all the other characteristics. It doesn't conduct electricity, like you said, it doesn't conduct heat, it's not shiny. Okay, so Play-Doh has some metallic characteristics, not all. What about non-metals? Are they ductile? Can you make them into a wire? No, they are still brittle. Metals are good conductors of heat. Non-metals are poor conductors of heat. Metals are good conductors of electricity. Poor conductors of electricity. Metals are found on the left side of the zigzag line. Non-metals are on the right side of the zigzag line. And metals like to give electrons, while non-metals like to take electrons. All right, we good? What are metalloids? Metalloids. Sometimes they're called semi-metals. They are on either side of the zigzag line. That's right. They have characteristics of both metal and non-metals. What's so important about them is that the non-metallic ones, like silicon, they have been made to be able to conduct electricity. And that was a huge development in electronics. Before we discovered how to dope silicon, that's the proper word, doping. That's adding metallic atoms into silicon in order to allow them to conduct electricity. Before we learned how to do that, we used vacuum tubes, which were like light bulbs. So a computer circuitry was made up of thousands of these light bulbs that had no air in them. The reason why they didn't have air in them is because as electricity runs through wiring, they produce heat. And they did these in these vacuum tubes because without air you can't conduct the heat. So you had computers that could multiply, add, divide, and subtract that were 3 stories tall because they had to use vacuum tubes. Once they discovered silicon, thanks to the space agents, the space race, once they discovered how to do this to silicon, then all of a sudden we could start miniaturizing these things. And by the early 80s, we had some computers that are like modern computers. And now, well, I was using a cell phone a few seconds ago, and that computer in there is like a bazillion times more powerful than the computers that were 3 stories tall. I mean, that's just amazing to me. Just amazing to me.
The computers on your phone was better than the ones on the spaceship.
You mean on the space shuttle? Yeah, in the early ones? Yeah, no doubt. How many elements have been discovered by the mid-1800s? About 60. about 60. The and 5 gases: hydrogen, oxygen, nitrogen, fluorine, chlorine, and 2 liquids: bromine and mercury. So who was the first to publish what became known as the modern periodic table? His name is Dmitri Mendeleev. Dmitri Mendeleev in 1869. Dmitri Mendeleev in 1869. Here's a picture of the old coot. He was a scary looking guy. But it's nothing. Hank Green does a fantastic job of explaining the life of Dmitri here.
Imagine you're in Siberia, and you're a 13-year-old boy, and your father, who was a professor but had gone blind, leaving your family of more than 10 brothers and sisters destitute, has just died. I know, downer. Your mom, to support the family, has reopened an abandoned glass-making factory in the small town where you live, largely because she wants to make enough money to send you to school someday. A year passes, the factory burns down. But your mom, she sees your potential. She knows that you have a keen scientific mind and will not see that squandered. So, with your siblings out of the house and on their own, she packs up your belongings, straps them to a horse, and with you in tow, rides 1,200 miles through the Ural Mountains on horseback to a university in Moscow. There, on your behalf, she pleads earnestly and effectively, and they reject you. So together, you ride another 400 miles to St. Petersburg, to the school where your father graduated as a scientist, and as luck, or extreme, insane, undeniably Russian persistence would have it, they accept you, and your saddle-worn butt, as a pupil. Your mother, having completed her mission, promptly dies. If you're doing your imagining as I've told you, you might feel a tremendous debt to your mother and a very deep desire to ensure that you achieve something on par with the sacrifices she made for you. And maybe that's one reason why Dmitri Ivanovich Mendeleev became the crown jewel of Russian science and a theorist who revolutionized how we see the world. Mendeleev spent a great deal of time in laboratories as a student, studying the burgeoning new field of chemistry. He worked with all the elements that you could work with at the time, and his knowledge gave him unique insights into their properties. Those insights would come in handy. Let's all imagine we're Mendeleev again. I like doing that. And that we know a bunch of stuff about chemistry, which, you don't yet. But we're imagining. So it's the 1860s, and about 60 elements are known to mankind, and their atomic weights are mostly known as well. So the simplest thing was just to sort them in order of their atomic weights. But interestingly, you, because you're clever pants, realized that the most significant relationships seem to have nothing to do with the atomic weight. Lithium, sodium, potassium, and rubidium were all extremely prone to reacting with chlorine, fluorine, iodine, and bromine. Beryllium, magnesium, calcium, and strontium were all similar but less reactive. But with a quick inspection, you, and to be fair, a number of other chemists, realized that there was a relationship between atomic weights, but it's periodic. At the beginning of the list of elements, characteristics repeat every 7 elements. On a side here, we now know that it's every 8 elements, but in the 1860s, elements were studied based on their reactivity, so the non-reactive noble gases had not yet been discovered, so the period occurred every 7 elements. As the mass of the elements increases, the repetition starts to look a little less periodic, though it's certainly still there, it just isn't perfect. Some of your colleagues, they're saying, well, such is life. It was perfect repetition early on, but later in the list it gets a little fuzzier. But not you. You become obsessed. Obsessed with the perfection of the periodicity. You write out the names and weights and properties of elements on cards, you lay them across your desk, shuffle them, tear them to pieces in frustration until one day you realize that you're simply missing cards. The numbers aren't working, not because there's something wrong with your ideas, but because some elements simply haven't been discovered yet. Armed with this insight, you insert gaps into the table, and things suddenly fall perfectly into place. 7 element periods for the first 2 rows with hydrogen in its own category, 18 element periods for the next 2 rows. You're so certain that you predict the properties of these missing elements, and when a French scientist comes along and says that he has in fact discovered one of them, you argue with him, saying that you discovered it first in your mind. And when you see his data, and it doesn't match yours, you publish a paper saying his data for the new element he discovered is wrong. That's how certain you are of yourself and this beautiful new theoretical framework you've created. And you know what the really crazy thing is? You're right! That French guy's data was wrong! You, never having examined the element he discovered, knew more about it than he did. Because you are Mendeleev, master of the elements. Okay, we're done imagining for the episode. That was fun, though. A lot of other obsessive scientists, Mendeleev never thought he was done with his table, so he held it back for quite a while, only publishing it as part of a new chemistry textbook he was working on as a way to make some quick cash that he needed. And as with many other scientific revelations, there were a number of other people hot on this discovery's trail. As many as 6 people published on the periodicity of elements at roughly the same time as Mendeleev, but a few things set him apart. One, he was obsessive. He knew the data better than anyone else and had spent a ton of time working on a theory that many people thought was just an interesting little quirk. And 2, he realized in a way no one else did that the idea of periodicity had far-reaching consequences. It seems as if he had a deep belief in the cosmic importance of what he was doing, almost a religious fascination. Mendeleev believed in God, but also he believed that organized religions were false paths to the unknowable nature of God. I like to believe that he thought he saw some divine pattern in his tables, and Mendeleev felt as if he was coming to know God in a way that no other man ever had. To be clear, this is pure conjecture. Our periodic table, as it stands, is really a little bit unhappy with itself, frankly. The lanthanides and actinides really should be part of the table, but we separate them out because it's hard to fit that on a piece of paper. Really, this is what it should look like. And really, it would be best if it wrapped around into a circle, so that fluorine and neon and sodium were all next to each other, instead of being on the opposite sides of the map, because they're just one proton away. Mendeleev's contribution, nonetheless, is more powerful than at first it seemed. He ended up forming a guide to help future chemists understand things that wouldn't be discovered for 25, 50, even 100 years. Indeed, after Mendeleev's theories were published and accepted, the overwhelming cry from the scientific community was, why? 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 And though Mendeleev was not himself concerned with this stuff, he actually denied the existence of atoms, or indeed anything he couldn't see with his own eyes, it turned out that the answer to the first why was the electron. That sneaky little electron, Mendeleev, if he'd been around to see their discovery, he would have hated them. But you will have a healthy respect for them after you learn all about them on the next episode of Crash Course Chemistry. Thank you for watching this episode of Crash Course Chemistry. If you were...
All right. If you ever want to watch Crash Course, it's really good. It's meant for more for AP Chemistry, but that's okay. So here's the old... Who did it remind you of? Is there a character in TV these days that Mendeleev, his arrogant Sheldon? It's just, and the thing is, most, not just physical, but just that arrogance. Unfortunately, probably some of the greatest scientists of all time were a lot like Sheldon.
Why do they all seem to have horrible backstories?
Yeah. Okay. So here's an example of the brilliance of Mendeleev. Okay, in his time, germanium did not exist. He found that the element that would have gone next in the periodic table did not really fit. So he presupposed that there was an element that had yet to be discovered. So he left it blank on his periodic table. He called it Ekasilicon, which means to come after silicon. Okay? And eventually, after he died, it was discovered, germanium. But look at his predictions as opposed to the real characteristics and properties of germanium. So he predicted a mass of 72, bam, 72.59. Density of 5.5, bam, 5.3, ain't bad. It's going to react with oxygen to form a formula of ESO2, well, GeO2. The density of that is going to be 4.7. It actually turned out to be 4.2. It's going to react with chlorine to form ESCl4, GeCl4. Bam! Right on the money. Density of that was going to be 1.9. Close. 1.8. He did this with at least 2 more elements with incredible accuracy. Okay? And that is why he became the father of the periodic table. Other people did this. Other people developed periodic tables that were similar. But no one was able to take it to the next step and predict elements that had yet to be discovered.
But he didn't make any elements, right? He didn't
No, no, he just predicted that they would be create, and he put our periodic table into its form that we see today. What does the periodic table function like? A calendar. What two properties did he use to construct his table? Atomic masses and the way they reacted with other elements. And how were the atomic masses of the elements determined? Well, basically, it's this simple. They said, okay, carbon is so important to us. We are mostly made up of carbon, or at least our solid part of us. We're carbon-based life forms. We will make carbon's mass 12. And then everything else was compared to it. So chlorine was 3 times heavier than carbon, so guess what became chlorine's atomic mass? 36. If you were 1/12 the mass of carbon, like hydrogen, then your mass was 1. What elements did these early chemists look to for helping them figure out how elements combined? Oxygen and chlorine. Oxygen and chlorine.